Good morning, everyone. I am Vinita, working as an associate professor in the Department of Electrical and Electronics Engineering, RMD Engineering College.
Okay, today I am going to explain about resistance earthing. So before going into earthing, let us discuss about the grounding or earthing. So what is mean by grounding? Grounding or earthing is nothing but connecting a frame of an electrical equipment to earth. This earthing, which is mainly classified into two types, ungrounded neutral earthing and neutral earthing. Ungrounded neutral earthing means without any connection between um, neutral and earth, the circuit that will be working. There is no earth connection. That is the meaning. And what is mean by neutral earthing? Neutral earthing means from the neutral of a three-phase circuit, there is a connection from the neutral towards the earth. It can be by means of various methods, by means of solid earthing. It may be by resistance earthing, reactance earthing, arc suppression or resonant grounding, using earthing transformer or voltage transformer earthing. So these are the types of, are the possible connections of neutral earthing. Today I am going to explain about resistance earthing. Let us discuss what is mean by resistance earthing, what is the need for this resistance earthing. So what is mean by resistance earthing? If a resistance which is connected between neutral and the ground, then it will be termed as resistance earthing. And here, um, what is the need for this resistance earthing? During any faulty condition, there may be a faulty current that flows through the circuit. That faulty current that may affect the power system components. Therefore, in order to protect the power system components from the faulty condition, the neutral earthing or the resistance earthing is provided, and so that the faulty current that will be taken to the ground through this neutral earthing. Now, let us assume that the fault has been occurred. Let us assume a three-phase circuit. For this three-phase circuit, the fault has been occurred at phase B. And the if the fault is occurred at phase B, normally the current that chooses during this faulty condition, the current that chooses this low resistance path. Now, since this path is short circuited, all the currents from the phases that will be chosen this faulty path. Now, this faulty current, which will consist of two currents, IR and IY. So, first, from phase R, the current IR that flows from phase R towards this faulty phase and then to the ground, then it will be flows to the corresponding capacitance CR towards the resistance point, towards the phase R. Similarly, from phase Y, the current IY that will be flowing from phase Y towards this neutral point, then faulty point to earth and through the capacitance CY and then the phase conductor Y. So these two are the two phase currents IR and IY. Similarly, the current from the faulty phase IF that will be flowing from phase B towards the faulty point, and then this current that will be flowing through the resistance R. Therefore, from this faulty point F, there are three currents. There are three currents IF, IR plus IY. So depends upon its internal resistance, these current will chosen its path and that will be flowing through its corresponding path. Therefore, this IF that will be flowing through resistance R and this IR plus IY that will be flowing through their corresponding capacitances CR and CY. Now, from this circuit, we can say that the current IF and IC, this is nothing but IC. IC is equal to IR plus IY. both these currents are in opposite direction, so that these two currents will try to cancel each other. The main objective of providing this resistance grounding is to avoid the arcing grounding. So as per the ungrounded neutral system, we have seen that there is a possibility of arcing grounds. So the arcing grounds are nothing but during the faulty condition, if the neutral earthing is not provided, there is an path between the faulty point as well as the ground. So once this path is ionized continuously, even though the fault is cleared also, the electrons that will be moving from the faulty point towards the ground. So continuously what will happen means there is a charging and discharging of capacitance occurs. So due to this, the voltages of that is the currents and voltages of the system may rises to very high value. So in order to avoid this arcing grounding, various types of groundings are provided. So here, as per this circuit and the working of this grounding system, these IF and IC both are in opposite direction, and so that we can able to eliminate the arcing grounds. And here, the value of R should neither be very low nor very high. That is, if the value of resistance is very low, the earth fault current that will be very high, and so the system that is acting as a solid grounding system. And if suppose the value of resistance R is very high, and the system that will be acting as an ungrounded neutral system. Therefore, for this system, the value of R should not be very low as well as should not be very high. Therefore, the value of R is chosen such that the earth fault current, which is limited to a safe value but still sufficient to permit the operation of the earth fault protection system. That is, we need to operate the protection system. For that, it requires some value of resistance R. So, in order to satisfy this condition, we have to select the resistance value. In practice, the value of resistance is selected such that it limits the earth fault current to 2 times the normal full load current for the 3-phase circuit. Now, we are going to draw the phasor diagram. To draw the phasor diagram, we need to apply the conditions. That is, the fault current IF can be resolved into 2 components. That is, the fault current IF2, IF1 and IF2. There are two components. One is IF1 and another one is IF2. IF1 is nothing but the current which is produced due to the reactive circuit. Here, this IF, which consists of 2 components. One is the current due to reactance, and another one is the current due to resistance. So this reactive component can be represented by IF2, and this resistive component which is represented by IF2, which is always in phase with the corresponding phase voltage. And IF1 is nothing but the reactive component which always lags behind their respective voltage by an angle of 90 degrees. Similarly, we have another one component IC. So this current IC, which always, this is nothing but a capacitive current, which always lead the capacitive phase voltage by 90 degrees. So with respect to these conditions, we are going to draw the phasor diagram. Here, first we can draw the 3 voltage vectors VR, Vy, and Vb. And the corresponding phase voltages are VBR, VBY, and here only we require VBR and VBY. So this is actually VBR and this is VBY. Since for the star connection, two currents are same. Here it is represented as IR and IY. So in order to get this phase voltages, here we'll be representing VBR and VBY. Now we can draw the two vectors IR as well as IY. So how to draw this vector IR? So we can consider VR vector. This is VBR. So for this VBR, its corresponding IBR that leads the voltage by 90 degrees since it is a capacitive circuit. Next one is VBY. So extend this line. Now for this VBY, its corresponding current IBY is leading by 90 degrees. This is VBY. For this VBY, its current is leading by an angle of 90 degrees. Now, if we join these two vectors, that is the vector sum of IR and IY gives the vector IC. And now we are going to draw the second vector IF. So we know IF is equal to IF1 plus IF2. That is, IF consists of resistive component and reactive component. Just now I have explained IF2 is nothing but an resistive component which always in phase with the voltage vector. Here this is nothing but an voltage vector VBN. For this VBN, its corresponding current vector will be in phase. So that's why it is represented like this. And for the same vector, it's the reactive component that is perpendicular. That is, it lags behind the voltage by an angle of 90 degrees. Now, if we join IF1 and IF2, we will be getting the voltage, we will be getting the resultant current IF. Therefore, as per this vector diagram, the capacitive current IC and the reactive current IF1 both are in phase opposition. Therefore, these two currents will try to cancel each other, and so the arc suppression, that is the arcing grounds, can be eliminated. And here we can discuss about the advantages and disadvantages. And as I said earlier, by providing the earthing resistance, the arcing grounds can be eliminated or it can be minimized. And by providing the value of resistance R, the earth fault current can be reduced. Therefore, interference with communication circuit can be reduced. So since the value of current is less, obviously it improves the stability of the power system. So these are all some advantages of resistance grounding. Next, if you take the disadvantages, during this resistance switching, there may be a possibility of displacement of the neutral. Therefore, the equipment has to be insulated for high value of voltages. And due to the, if the value of resistance is very low, the system will be acting as a solid grounded system. For that solid grounded system, we need to provide high insulation. Therefore, the system becomes costlier. And due to the provision of resistance, there may be a possibility of power losses. So these are all some disadvantages of resistance switching. And if you take the applications, this resistance grounding can be operate in the voltages of 2.2 and 33 kV with a capacity of 5000 kVA. So this is till 5000 kVA. That is, this is nothing but a high value of rating of three-phase system. Until this 5000 kVA, we can go for using this resistance switching. So these are all about resistance switching. Therefore, the main objective of providing this resistance switching is to reduce the effect of arcing. Thank you.